In this lesson, we're going to look at the law of sines again, which, if you remember, says that the sine of an angle is to its opposite side as the sine of another angle is to its opposite side. The sine of the third angle is to the side opposite that. And in a previous lesson, we looked at where we were given two angles and a side, and we were able to solve the triangle. Well, in this lesson, what we want to do is look at when we're given two sides and an opposite angle, an angle that's opposite one of those sides. Now, this is going to be called the ambiguous case. Ambiguous just simply means that it's not clear. And so what we're going to find that what's not clear in this is how many triangles we have, or if we even have a triangle. Now, the situation, and I want to try to draw this, what I always like to do is think of one of those scoops that digs out the earth. So if we have a side, and we have a second side. And I'm going to try in each one of these to draw them the same. Now, what we have here then, if we think of our ground, it's going along here. Just go ahead and put it for all of these. So in this case, we have our angle with the ground. So we have two sides and the angle opposite one of them. Well, you've seen those scoops and it's hanging up in the air and you don't have a triangle. So in this case, we can have two sides and an angle opposite one of those and not have a triangle. Now we could take those same two sides, and at night, if you think about what ends up happening, so we've got our side the same length, and this one's the same length. Well, at night, a lot of time what happens is they end up setting it on the ground. And what we changed here was this angle, but we still have two sides and an opposite angle, and we have a triangle. And we know that that's not part of it. So we have one triangle. Now, when that scoop starts trying to work, you think about it, it extends itself out. And then what happens is the scoop will swing forward to scoop out some earth. It hits the earth there. Then it swings back and it comes up here, and then it's lifted up. So in this case, we have a triangle here, but we also have a triangle over here. Now our angle back at the first, where our scoop is on the ground, didn't change. And the length of our sides didn't change, but we see that we could actually have two triangles. We could have one here. We could have one here. And so it scoops down into the ground to dig out the earth, but we can actually end up with two triangles. So this is why this is called the ambiguous case. Given two sides and an angle opposite one of those sides, we might not have a triangle at all. We may have a triangle, or we may end up with two triangles. And so we don't know when we start. Now, if you'll look in your book, most of the time they give you a table of how the sides relate, where if the side opposite the angle is shorter than the other side, or if it's longer, or if the height of the triangle, and where you can know how many triangles you have. I've always found that to be fairly confusing, and in many times you have to solve for one of the sides. What I like to do is to assume that there's going to be two triangles. And as you go through and work these, if there's no triangle, it's going to show up immediately. If there's only one triangle, it will show up fairly quickly. And if there's two triangles, then you've gone ahead and solved for it. And I find that it's really not extra work to do it that way. And to go ahead and figure up how many triangles there's going to be, sometimes you have to do computations, then you still have to solve the triangles. So if you want to look in your book and see the table and go through and figure that, you can, or we can just go ahead and work these. So let's look at a problem. Let's say that we were given that we have an angle that's 44 degrees, a side that's 30 feet, and then another side that's 38 feet. Okay, we want to solve this. So we're going to draw our triangle, and we're just drawing one triangle. That's a pretty sloppy triangle. So let's draw us a triangle. And I don't try to draw it to scale. I just draw me a triangle. And we're going to label it A, B, C. So we know that angle A is 44, side A is 30, side B is 38. So in this case, we have two sides and an opposite angle. That's going to tell us this is the ambiguous case. We may end up with one triangle, two triangles, or no triangle at all. So as we go through, what we can solve for is angle B. So we're going to set up our ratio. The sine of 44 degrees is to the opposite side, as the sine of B is to the opposite side. So we can do the product that we can do. We have 38 sine 44 is equal to 30 sine B. And so 38 sine of 44 divided by 30 is the sine of B. Now, if you remember what we end up having to do here then, since we're solving for an angle, we're going to have to do the inverse sine. So let's look at our calculator. And make sure that we're in the degree mode. Okay, as we do that, let me move this over so we can see our work. We have 38. Now, you can do this one of two ways, and most of the time I forget about doing my inverse sine first. So we can do 38 times the sine of 44 divided by 30, enter. Now that's the sine of angle B. So now we've got to go back and say second sine, and we can just do second answer. It'll pull that answer back up. And so we get that angle B is 62 degrees. Now if you can remember to do this, since we're looking for the angle, you could have done second sine. It puts parentheses, and in parentheses you put your computation. 38 sine 44 divided by 30. Close your parentheses, enter, and it will go ahead and give you the angle. But a lot of times as I'm starting my proportion, I don't always think to put that first. So if you don't, then all you have to do is say second sine or inverse sine and then second answer, and it will pull that back up. So we get that angle B is 62 degrees. But the problem is our sine was, this was positive. When we went back and we were looking at that, let me just pull my calculator back up. We got that computation, our function was positive. The sine is positive in the first quadrant, but it's also positive in the second quadrant. So we don't know from this if we're supposed to be in the first quadrant or the second quadrant. That's where the ambiguity comes in. So what we have to do is figure it for both. If it's in the first quadrant, angle B is 62. If it's in the second quadrant, then we're going to have to do 180 minus 62. 62 would be our reference angle. So if our angle is supposed to be in the second quadrant, then angle B could be 118 degrees. The way we show that is we're going to put a little subscript. So angle B could be 62 degrees if it was in the first quadrant, but if it's supposed to be in the second quadrant, it could be 118 degrees. Now what we have to do is go through and work our triangles for both. I'm going to go through and work it for 62 degrees because I know definitely that there is a triangle for that. So what I need to do is figure up what angle C is. I know angle A. I found that angle B could be 62. So for angle C, I'm going to subtract. So I'll do my 180 minus 44 minus angle B, which was 62. So in that case, angle C would be 74 degrees. So I'll get angle C is 74 degrees. Okay, now I can find side C. So I'll set up my ratio. The sine of 44 is to the opposite side, as the sine of 74 is to side C. And I can use my calculator and get my proportion there. I'm going to get the product that I can, so I've got 30 sine 74 divided by the sine of 44. This is just doing the regular law of sines. And so I get that side C would be 42. And that would be 42 feet. Now I have to go back though and say, but angle B could have been 118 degrees. If angle B was 118 degrees, then angle C, and notice I'm putting subscripts because this is a whole different triangle, then angle C would be 180 minus, I believe it was 44 degrees, was angle A. That didn't change. But now angle B is 118 degrees. And so in that case, angle C would be 18 degrees. And I need to figure out then what side C would be. The sine of 44 is to 30, as the sine of 18 is to C sub 1. So getting the product I can, 30 sine 18 divided by the sine of 44, then C would be 13. So this is what you have to do when you're given two sides and an opposite angle. You have to consider that you don't know how many triangles there are. I've always found if you'll just go ahead and assume that there's two, then you're going to be able to solve it and you won't forget about that second triangle. So in this case, we did have the possibility of two triangles. Angle B could have been 62 degrees, or angle B could have been an acute angle and been 118 degrees. All right, let's look at another one. And in this one, we're going to see that angle C is 35.4 degrees. Side A is 205 feet. And side C is 314 feet. So we draw our triangle. We're going to label it. So angle C was 35.4. Side A was 205. And side C was 314. So looking at what we've been given two sides and an opposite angle. We're going to use the law of sines, but this is our ambiguous case. So let's find angle A. So we would say the sine of 35.4 is to 314 as the sine of A is to 205. Now remember, we can do the product that we can get. And if you remember, you can go ahead and do your inverse sine. Let's try to do that. So let's do second sine because we're looking for an angle. So we get the product that we can, 205, sine 35.4 divided by 314. So we get that angle A is 22.2 degrees. If it's in quadrant 1, but it could be in quadrant 2. This is angle A. So if it's in quadrant 2, then it would be 180 minus 22.2, because 22.2 would be my reference angle. So it could be 157.8. Now, I'm going to go through and solve it as if it's 22.2. So I have angle A, I have angle C. I can then find angle B by subtracting. So I have 180 minus 35.4 minus 22.2. So angle B would be 122.4. And I can find side B. So I'll set it up. The sine of 35.4 is to 314 as the sine of 122.4 is to B. So we will get the product that we can. So 314 times the sine of 122.4 divided by the sine 35.4. So we get that B is 458. So B is 458, and that's feet. Now that was if A was 22.2 degrees, but we said that A could also be 157.8. So let's go through and solve. So we'll need to find angle B. Well, to find angle B, we'll take 180 minus the 35.4 minus angle A, the 157.8. And if you'll notice, what we get is negative 13.2 degrees. Well, we can't have a negative angle in a triangle. So it's saying that this angle's too big along with this angle to leave you enough degrees. These two angles add up to be more than 180. So that means that we only have one triangle. Angle A could not be 157.8. So we only have one triangle, and we didn't have to do that much extra work to find that. So I always go through and assume that I've got one, and I'll go ahead and solve that one, because if I have an angle here, then I'm going to have at least one triangle. Then I go back and I solve it, well, if it were the other angle. And if it's not, it shows up right away. Okay, let's look at another problem. Say that we were given that angle A was 30 degrees, angle B was 40 feet, and, or not angle B, side B, and side A is 10 feet. Okay, we're going to draw us a triangle. And we'll label our triangle. So angle A is 30, side B is 40, and side A is 10. So we have two sides and an opposite angle. So this is our law of sines, but it's our ambiguous case. So we know that we may have two triangles. So we're going to find angle B first. Well, we do the sine of 30 is to 10, as the sine of B is to 40. So using our calculator, we'll do 40. Let me clear that off. We'll do 40 sine 30 divided by 10. Oh, okay, we forgot to do second sine, second answer. Notice it gives us an error, and the error was a domain error. Well, let's go back and see why. Let's go back and look at what we had up here. We had this problem when we hit enter. Notice we got 2. There's no angle whose sine is 2. Remember, the largest that a sine can be is 1. It goes from -1 to 1. So that's why we ended up with an error, which means we have no triangle. So if you go ahead and start solving it, it's going to show up right away. If you have no triangle, you'll get an error message. If you only have one triangle, well, you're not going to have enough degrees for the other. And if you have two triangles, then you will have solved it. Now, if the angle you were given was an obtuse angle, if the angle we had been given to begin with was greater than 90 degrees, it was an obtuse angle, then the most we can have is one triangle. So sometimes we can use some common sense there. Let's look at a couple more. Say that angle A is 20 degrees, side B is 40, and side C is 30. So we draw our triangle. A is 20, B is 40, and that should be A, not C. I need a side opposite. So this is angle or side A. So we have two sides and an opposite angle. So this we will use then our law of sines, and we know it's the ambiguous case. So the sine of 20 is to 30 as the sine of B is to 40. Okay, we're going to solve for B. Now, since we're solving for an angle, if we can remember, we can go ahead and put second sine, and then we get the product that we can, 40 sine 20 divided by the other, which is 30. So we get 27 degrees. So B would be 27 degrees. If it's in the first quadrant, now I go ahead and find what it is if it's in the second, because then that way I've got it written down, and after I do my other computation, I don't forget about it. So if it's in the second and 27 was my reference angle, 180 minus 27 is 153 degrees. Okay, so I've got two separate ones. I'm going to go through and solve it as if it's 27 degrees. So I know A, B, I need to find angle C. Well, that's going to be 180 minus 27 minus 20, which is 133 degrees. And then I need to find side C, so I'll set up my ratio. The sine of 20 is to 30 as the sine of 133 is to side C. So we'll get the product that we can, which would be our 30 times the sine of 133 and divide by the sine of 20, which is going to be 64. So that means that side C would be 64. Okay, but we said that it could be 153 degrees. I'm going to go through and put these in a different color just so that we can notice that we have two different ones. So angle B, we said, could also be 153 degrees. So that would mean that angle C would be 180 minus the 20, that was our angle that was given, minus 153, which is 7. So in this case, we are going to have a possibility of two triangles. So C could be 7 degrees, B is 153 degrees, and A is 20. So now I have to figure up, okay, what would side C be there? So the sine of 20 is to 30 as the sine of 7 is to side C. So 30 sine 7 divided by sine 20. And we get 11. So C would be 11. And that's 11 feet, whatever our units are. So here again we had two triangles. Let's look at one last one, and then we're going to look at something called heading and some applications. Let's say that B is 46 degrees, 10 minutes. Side B is 1.75 feet, and side C is 1.14 feet. Okay, we'll draw us a triangle. It's not too bad. Okay, angle B, A, C. So B is 46 degrees, 10 minutes. Side B's 1.75. And side C is 1.14. Okay, we have two sides and an opposite angle, so this is the ambiguous case, so we'll set it up. The sine of 46 degrees, 10 minutes, is to 1.75. As the sine of C is to 1.14. Okay. And again, I'm going to try to remember to do my second sine. If I don't, then at the end I can do second sine, second answer. So I've got 1.14 sine of 46, second angle number 1, 10 minutes, so second angle number 2, divided by 1.75, enter. So I get that angle C is 28 degrees. Now, this was off to the nearest 10 minutes, so let's just see what this would be to the nearest 10 minutes. It turned out to be 28 degrees to the nearest 10 minutes. So angle C is 28 degrees. Now, that's if it's in the first quadrant. If it's in the second quadrant, then it would be 180 minus 28, which is 152 degrees. Okay, so we're going to go through and solve it. As if angle C is 28 degrees. Then we'll come back and solve it for the 152. So if angle C is 28 degrees, then angle A is our 180 minus 46 degrees, 10 minutes, minus, I didn't need the parentheses there, minus 28, which was angle C. And doing second angle number 4, we get 105 degrees, 50 minutes. Okay, and then we solve for side A. So we'll set up our proportion. The sine of 46 degrees, 10 minutes, is to 1.75, as the sine of 105 degrees, 50 minutes, is to side A. So getting our product, 1.75 sine 105 degrees, 50 minutes, divided by sine 46 degrees, 10 minutes, gives us 2.33 feet. So A is 2.33 feet. Okay, let's go back then in case angle C was 152 degrees instead of 28. So in that case, we need to find angle A, which would be 180 minus 46 degrees, 10 minutes, minus 152 degrees. And again, we've ended up with a negative angle, which means there's not enough degrees. 46 degrees, 152, that was more than 180 degrees. So we can't have that second triangle. So in this case, we only have one triangle. Right, this is solving then given two sides and an opposite angle. And you need to remember in those cases, you may end up with no triangles, you may end up with one triangle, or you may end up with two triangles. What I recommend you do is you assume there's going to be two. If there's not any, it shows up immediately. You get an error message when you're trying to get your angle. If there's only one, well, it shows up fairly quickly. When you try to get your other angles, you run out of angles and end up with negative. Okay, we want to look at a couple of types of applications, and we need to look at a definition. This deals with heading. The heading of an object is the angle measured clockwise from due north to the vector representing the path of the object. Now we've looked at how to do directions other ways using your north-south and your east-west line, where you go north 20 degrees toward the east or north 50 degrees toward the west. This is another type that's used a lot by pilots for navigation because they're using their magnetic compass that points to north, and then they can rotate around 360 degrees. So if we're using this, if we wanted to draw the heading of 80 degrees and our vector, the length of it's 20 miles. We're going 20 miles in a direction of 80 degrees, or a heading of 80 degrees. Okay, we think of north, and let's make that a little better. So we've got our north-south line from north. Now what our heading does is it starts at north and we go clockwise. We wouldn't be quite 90 degrees. So we have 80 degrees, and the length of our line represents the magnitude of our vector. So we've got 20 miles. If we wanted to draw one that was 215 degrees and 20 miles, okay, we would start with our north-south line. Then from that, we would rotate around 215 degrees. Well, due south would be 180. Due west is 270, so we've not quite gone that far. So there would be our angle 215 degrees, and then the magnitude of our vector would represent the length of the line would represent the magnitude of our vector. And so we have problems with navigation where we're dealing with these. We're going to look at a few here, and we'll look at a lot more in the next section when we get into our law of cosines, and we'll deal with those. But let's look at a couple of problems. And this first one says that a boat is headed due north at a constant rate of 16 miles per hour. Because of the current, the true course of the boat is 15 degrees. If the currents are a constant 14 miles per hour, in what direction are the currents running? Okay, we have a boat that's headed due north. So it's going north. And it's going north at a rate of 16 miles per hour. So that's going to be our magnitude. Now, that's what it's trying to do according to its instruments. Heading is always what the instruments are saying. But we have currents, and we know that the currents run and they can push you different ways so that you're not on course. Well, that's what's happened here, is the true course is actually 15 degrees. So the course is actually going off here 15 degrees. Now, what we want to know then is about the currents. Well, it tells us that the magnitude of the current was 14 miles per hour. So let's just say from north, wherever it is, we're going to draw the magnitude of the current, but we don't necessarily know the angle. So our currents are going at a rate of 14 miles per hour. Okay, what we want to know then is what's the direction from north. What's the direction around to our current? Well, let's look at what we know. We've got that this angle inside is 15. We know that much. So what we have are two sides at an opposite angle. And we're needing actually this angle outside because we're needing our heading, what direction the currents are going, and it always goes from north. But since we know this is a north-south line, because the boat was going due north, that was what the instrument said, then if we could find this angle inside, we could subtract from 180 and get what our heading was, or what the heading of the currents were. Well, we've got a side. We know the opposite side. We have a side. We could find this angle over here, and that would then give us two angles. We can subtract and get the third angle. So let's set this up. But we also know this is the ambiguous case. So the sine of 15 is to 14 as the sine, and let's just call this alpha, as the sine of alpha is to 16. So we have second sine, 16 times the sine of 15 divided by 14. So we get that alpha could be 17 degrees. But we also know this is the ambiguous case, so let's go ahead and see what else it could have been. 180 minus 17. It could also be 163 degrees. So alpha could have also been 163 degrees. Okay, so let's go through and solve it for both. If alpha was 17 and this is 15, then our angle would be 180 minus 15 minus 17. Okay, our angle up here, which let's call that angle up there beta. So beta, and remember that angle we're talking about what's inside. would be 148 degrees. Now, that's what the angle inside. To know what the currents were running, remember we're going to have to subtract that. We know that this is a north-south line. This angle's 148, so that would mean 180 minus 148. That would mean that our currents were running on a heading of 32 degrees. So the current would be 32 degrees. So let's just draw that more in line with what happens. The boat is going due north. I have trouble drawing straight lines. The boat's going due north. Now your currents are running at 32 degrees. So from north, your currents are running off in this direction, 32 degrees. And we know that they were 14. So since I drew that line, other line so long to represent the magnitude, need this one pretty long. So that means then the boat is actually going to go in this direction. So it's off by 15 degrees. Now we said it could have been 163. So let's see what that would be. We would have 180 minus 15 minus 163. So that would mean that our angle inside, beta, would be 2, which would mean then that our currents, okay, this angle's 2, so this angle would be 180 minus 2, or 178 degrees. Okay, let's look at what that means. So if we had that, okay, again, our boat's going due north. Now the current is running in a direction of 178 degrees. So from north, circling around, 178 degrees gets our currents going off in this direction at 14, so just a little bit less, which puts our boat going in this direction. And you can actually see from the lengths of the vectors, if I've drawn them a little kind of correctly, in this way the boat would be slowed down a lot because the boat's going against the current. In this one, the boat's kind of going with the current, and notice it would be sped up. And in some of our later problems, we'll actually see then about what that does to the speed of the boat. Okay, and let's look at one more problem where we could solve. We've got a boy is riding his bike on a road that runs east and west. He leaves the road at a house and rides 5.25 miles in the direction of north, 15.5 degrees east. We're using the other kind of measuring now. Then he turns to his right and rides 6.5 miles back to the road where he has a flat. How far will he have to walk to get back to the house? Okay, there's a road that runs east and west. There's the road. Okay, the boy's riding along, and he decides at a house to leave the road and to go from the north. Okay, from the north, he's going 15.5 degrees toward the east. And he rides for 5.25 miles. Okay, then it says he turns to his right. It doesn't tell us the direction. It's just somewhere to his right. and he rides back to the road. Now, see, what we don't know is just where he hits the road. Oh, so he rides back to the road, and he rides 6.5 miles. So we do know how far he rode. So 6.5 miles. Okay, and here he has a flat. What we want to know is how far does he have to walk to get back to the house? Now, we know that this direction, this angle, was 15.5. But notice that's outside our triangle. But since this was an east-west line, we can do 90 minus 15.5. So this angle is 74.5 degrees. Well, what we have now are two sides and an angle opposite. So we can do some solving to be able to find a few things. So we can start off, we can find our angle here. Let's call it alpha. So the sine of 74.5 is to 6.5 as the sine of alpha is to 5.25. So we've got 5.25 sine 74.5 divided by 6.5. Okay, now we're needing the angle, and I didn't put it first, so I'm going to put second, sine, second, answer. So that gives me an angle of 51.1 degrees. So alpha would be 51.1 degrees if it's in the first quadrant. But alpha could have been in the second quadrant, so it could have been a 51.1 could be my reference angle. So I'll subtract. So it could also have been 128.9. Okay, let's go through and solve it as if it's 51.1. If it is, then I can get my third angle. So I'd have 180 minus 74.5 minus 51.1. So I get 54.4. And let's call that angle up there beta, or B. Okay, that was 54.4. Once I know that, then I can get my side B. So I have the sine of 74.5 is to 6.5 as the sine of 54.4 is to B. So 6.5 sine 54.4 divided by the sine 75.4. Okay, I get that he would be 5.5 miles from home. So B would be 5.5 miles. Okay, that's if my angle was 51.1 degrees, but it might be 128.9. So let's go see through that and see how far he would have to be. So we have 180 minus 74.5 minus 128.9. And you've probably already noticed that you're going to run out of degrees. So that means that there was only the one triangle and our angle could not be this. So he's going to be 5.5 miles from home. Okay, this is another way of using the law of signs, but we remember that it's the ambiguous case. We're given two sides and an opposite angle, and when that's what we have may have no triangles, one triangle, or two triangles.